next theorem, and that depicts the order completeness of real numbers. So order completeness in set of real number, this means what? Every non-empty set of real numbers which is bounded above always has supremum, or you can say least upper bound, in R. So this is the meaning of order completeness in R. We know that our set of real numbers, they are field. We know that set of real numbers, they are ordered field. Now the next is completeness. Completeness means here that every non-empty set of real numbers which is bounded from above, that always have a supremum in R. Supremum bhi exist karega if it is bounded from above, right? So this is the order completeness property in case of real numbers. What can be said about the set of rational numbers? Are they order complete?
Ma'am.
No.
No, right? They are not ordered complete, means there may exist a set of rational numbers which are bounded from above, but they have no least upper bound in set of rational numbers, right? In R में तो होगा, but in set of rational numbers जरूरी नहीं है. और ये हमने किया है केस, हमने ये केस किया था कि you are having a no rational number whose square is 2. So you can consider a set where the squares are less than 2. So we can prove this. This is very important result. The set of rational numbers this is not ordered complete. Means there exists a non-empty set of rational number which is bounded from above but does not have a supremum in rationals, right? So what do we want to show? That it is sufficient to show that there exists a non-empty set S of rationals which is bounded above but does not have a supremum in rationals. रियल होता तो ट्रू हो जाना था, बट रैशनल्स में जरूरी नहीं है कि सुप्रीमम एग्जिस्ट करे. So therefore the set of rational numbers, they are not order complete. So how to prove this? Can I move to the next slide?
Yes, ma'am.
So now just see, let S, हमने एक set consider किया, be the set of all those positive rational numbers whose square is less than 2. Means S हमने set लिया उन सभी rational numbers का which are greater than 0 and S square is less than 2. Now clearly your S is non-empty. Why it is non-empty? Because 1 belongs to set S. 1 is greater than 0 and 1 square is less than 2. So we are having a rational number 1 which is belonging to this set S. So clearly this set is non-empty. This point is clear.
Yes, ma'am.
Also, this set is bounded from above. This set is bounded from above. Why? Because 2 is an upper bound. Right? Every element of the set S is less than 2. अगर स्क्वायर लेस देन 2 है तो एलिमेंट भी आपका लेस देन 2 हो जाएगा, मींस 2 जो है दैट विल बिकम द अपर बाउंड फॉर द सेट S. So if we are having an upper bound, it means our set is bounded from above. This point is clear.
Yes, ma'am.
So what we have that S is a non-empty set of rational numbers which are bounded from above. Now what we want to prove that? We want to prove that there exists a least upper bound, or you can say supremum, and that is a member of S. Right? So we want to prove this thing. अगर ये चीज होल्ड हो गया तो आपका ऑर्डर कंप्लीट आ जाएगा, अगर ये नहीं होल्ड होगा तो ऑर्डर कंप्लीट नहीं होगा. राइट? So for this we assume that, let if possible, the rational number k be the least upper bound of the set S. Now clearly your k is greater than 0, and also one and only one property hold होगा by the ordered set, that either k square is strictly less than 2, it is equal to 2, और थर्ड केस इट इज ग्रेटर देन 2. सो इनमें से एक पॉसिबिलिटी जरूर होल्ड होगा, बिकॉज आपका सेट ऑफ रैशनल नंबर्स ऑर्डर्ड सेट है. राइट? Also one and only one of these three holds. So now we consider the first case, that k square is less than 2. So for this we consider a positive rational number. Let us consider a positive rational number y of the form 4 plus 3k divided by 3 plus 2k. So we consider this rational number, positive rational number. Now just see, we get a contradiction or not. Can I move to the next slide?
Yes, ma'am.
Okay. So now you take the difference of k and y. Substitute the value of y over here. It is 4 plus 3k upon 3 plus 2k. Simplify this. What will you get? Now just see, this is positive number, this is positive number. What about this? What about this? Your k square is less than 2. So k square minus 2 will be,
Negative. Negative.
yes, it is less than 0. So the whole number will be negative. So this implies what? Your k is less than y. Further, what will be your 2 minus y square? To simplify this, now after simplifying, what will you have? This 12k, 24k cancel out. This is 8k square, this is minus 9k square, so you get minus k square. 18 minus 16, so 2 minus k square upon 3 plus 2k whole square. Now clearly this is positive, and 2 minus k square is also 2 minus k square is also positive. This point is clear. From here, 2 minus k square will be greater than 0. So the whole number is strictly greater than 0. So that means 2 minus y square is greater than 0, which means y square is less than 2. So that means your y is also a member of S. This point is clear.
Yes, ma'am.
Yes, ma'am.
So you get a rational number, positive rational number, which is a member of this set, and it is greater than least upper bound. Is it possible?
Ma'am.
You suppose that k is the least upper bound of the set, but we get a number which is greater than least upper bound and which is also a member of the same set as. It's not possible, right? So that means our supposition is wrong. Thus, the member of S is greater than k, which contradicts that k is the least upper bound of S. So that means this case is not possible, right? So this case is not possible. Which case? Which case?
K
K
square is
square
less
K
is
than 2.
square less
than
than 2.
2. This is not possible. So we consider the next case, case 2, that k square is exactly 2. This case you have already proved. आपने ये प्रूफ किया है, there does not exist any rational number whose square is equal to 2. तो ये केस तो अपने आप पॉसिबल नहीं होगा, because we cannot find a rational number k whose square is 2. So you can give the proof of that case over here, right? So we have already proved that there does not exist any rational number whose square is 2. So this case is also not possible. Case third, we will assume that k square is strictly greater than 2, right? Again, we choose the rational number y to be as same as that 4 plus 3k upon 3 plus 2k as a positive rational number, right? Again, we find out k minus y. Now just see, already you have Simplify this, that k minus y will become 2 times k square minus 2 upon 3 plus 2k. So you can substitute over here. It is twice time k square minus 2 upon 3 plus 2k. Now again this number is positive and k square minus 2 is also positive. So you get this is positive. Is this point clear?
Yes, ma'am.
Yes, ma'am.
Again we choose the rational number y as this one, and first we consider the difference of these two, and from here we get y is strictly less than k. Right, now we will find out 2 minus y square. Again after simplifying as previous we have done, it will become 2 minus k square upon 3 plus 2 k whole square. So you can substitute 2 minus k square upon 3 plus 2 k whole square. Denominator is positive, and what is 2 minus k square? It is strictly less than 0. So that means this is less than 0. Now this implies what? 2 minus y square is less than 0, which implies 2 is less than y square. So y square is greater than 2. Again you get contradiction. Now what contradiction? Here you are having a number y which is less than k, and where k is the least upper bound of the set S. If your k is the least upper bound of the set and y is less than this number, then clearly y belongs to class S. Y belongs to set S because it is a rational number and it's satisfying this thing. Is this point clear?
Yes, ma'am.
So y, if your y is a member of S, its square cannot be greater than 2 because our class S, our set S is defined like this. It is a set of all those rational numbers which are strictly greater than 0 and its square is less than 2, right? So this cannot be possible that your y is less than k and y square is greater than 2. It means k cannot be the least upper bound, y should be the least upper bound. Is this point clear? Right, so from here what you have, if your y square is greater than 2, it means y is upper bound of S, right? But k हमने assume किया है least upper bound of set S, and your y is less than k. This gives you contradiction. This is not possible. You get an upper bound which is less than least upper bound. That is not possible. This point is clear. This is not possible. Clear to everyone?
Yes, ma'am.
Hence none of the case is possible. So from here what you get? That our position is wrong. That means there does not exist least upper bound. This is k as a rational number for the set S. And this shows that, yeah, this proves that the set of rational numbers, they are not order complete. Is it clear to all of you?
Yes, ma'am.
But same set अगर हम real numbers में लेते, Clearly this set is bounded from above by the bound 2, right? And it is non-empty because 1 belongs to this set S. So there exists a least upper bound which is member of a real number. There always exists a least upper bound in R. Here the least upper bound is square root of 2, and clearly that is a real number.